Okay, section 10.3. Welcome to the last lecture of the semester. It might be a little bit longer because we have, I believe, 10.3, 10.4, and 10.5, with two of them being pretty big, but we will persevere, get it in the books. Testing and estimating a single variance or standard deviation. Go ahead and look at the focus points. Testing sigma squared. Many problems arise that require us to make decisions about variability. In this section, we will know two kinds of problems. One, we will test the hypotheses about the variance or standard deviation of a population. And two, we will find confidence intervals for the variance or standard deviation of a population. It is customary to talk about variance instead of standard deviation because our techniques employ the sample variance rather than the standard deviation. Of course, the standard deviation is just the square root of the variance, so any discussion about variance is easily converted to a similar discussion about standard deviation. Let us consider a specific example in which we might wish to test a hypothesis about the variance. Almost everyone has had to wait in line. In a grocery store, bank, post office, or registration center, there are usually several checkout or service areas. Frequently, each service area has its own independent line. However, many businesses and government offices are adopting a single line procedure. In a single line procedure, there is only one waiting line for everyone. As any service area becomes available, the next person in line gets served. The old independent lines procedure has a line at each service center. An incoming customer simply picks the shortest line and hopes it will move quickly. In either procedure, the number of clerks and the rate at which they work is the same, so the average waiting time is the same. What is the advantage of the single line procedure? The difference is in the attitudes of the people who are waiting in the lines. A lengthy wait line will be more acceptable even though the average waiting time is the same, if the variability of waiting times is smaller. When the variability is smaller, the inconvenience of waiting, although it might not be reduced, does become more predictable. This means impatience is reduced and people are happier. To test the hypothesis that variability is less in a single line process, we use the chi-square distribution. Find the chi-square value that the area to the right of the chi-square is 0.05 when degrees of freedom equal 10. Since the area to the right of the chi-squared is to be 0.05, we look at the right tail area equal to 0.050 column, and with the row degrees of freedom equal 10, chi-squared is equal to 18.31. See figure 10.6a. All right. Find the chi-squared value such that the area to the left of chi-squared is 0.05 when degrees of freedom equal 10. When the area to the left of chi-squared is 0.05, the corresponding area to the right is 1 minus 0.05, which is 0.95. So we look in the right tail area 0.950 column with the degrees of freedom of 10, and we find a chi-square equal to 3.94, figure 10.6b. Okay. Go ahead and pause the video so you can take down your procedure. All right, confidence interval for variance. Sometimes it is important to have a confidence interval for the variance or standard deviation. Let us take a look at the example. Mr. Wilson is a truck farmer in California who makes his living on a large single vegetable crop of beans, green beans to be specific. Because modern machinery is being used, the entire crop must be harvested at the same time. Therefore, it is important to plant a variety of green beans that mature all at once. This means that Mr. Wilson wants a small standard deviation between maturing times of individual plants. A seed company is trying to develop a new variety of green bean with a small standard deviation of maturing times. To test the new variety, Mr. Wilson planted 30 of the new seeds, carefully observed the number of days required for each plant at its peak maturity. The maturing times for these plants had the same standard deviation S equal to 3.4 days, how can we find a 95% confidence interval for the population standard deviation of maturing times for this variety of green bean? To answer this question, the answer to this question is based on the following procedure. So, pause the video and take down your requirements. Pause the video and take down your procedure. From figure 1210, we see that the C confidence level on the chi-square distribution with equal probability on each tail does not center the middle of the corresponding interval under the peak of the curve. This is to be expected because a chi-square curve is skewed to the right. A random sample of n equal to 30 green beans plants has a sample standard deviation of S equal to 3.4 days for maturity. Find a 95% confidence interval for the population variance. Assume the distribution of maturity times is normal. To find the confidence interval, we use the following values. C equal to 0.95, n equal to 30, degrees of freedom equal to 29, S equal to 3.4. To find the value of chi squared, the upper value. That's going to be upper and lower bounds. We use table 7 of appendix 2 with degrees of freedom 29 in the right tail area, 1 minus C divided by 2, which is 0.025. From table 7, we get the upper bound of 45.72. To find the lower bound, we're now going to change it to a plus, and it'll be 0.975. From the table 7, we get something. We get cut off, so you'll have to check it out in the book yourself or on digitally. From Formula 1 tells us that our desired 95% confidence interval is, and here luckily they will fill it in for us. So your lower bound was 16.05. So you end up with 7.33 and 20.89. Then if you take the square roots, so 2.71 and 4.57. All right. Trying to finish this one up as quick as I can. Overview of the F distribution. The F probability distribution was first developed by the English statistician Sir Ronald Fisher. Fisher had a long and distinguished career in statistics, including research work at the agricultural station at Rothamsted. During this time, there he developed the subjects of the experimental design and ANOVA. The F distribution is a ratio of two independent chi-square random variables, each with its own degrees of freedom. Okay. The F distribution depends on these two degrees of freedom, numerator and denominator. 1013 shows a typical F distribution. Go ahead and write the properties of the F distribution. The degrees of freedom used in the F distribution depend on the particular application. Table 8 of Appendix 2 shows the area and the right tail of different F distributions according to the degrees of freedom in both the numerator and denominator. Table 1014 shows an excerpt from Table 8. Notice that the degrees of freedom for the denominator are row headers. For each degree of freedom for the denominator, right tail areas from 0.1 down to 0.001 are provided in the next column. Then under column headers for degrees of freedom for the numerator, values of F are given corresponding to degrees of freedom denominator, the right tail area, and degrees of freedom for the numerator. For example, degrees of freedom denominator equals 2, right tail area 0.010, and degrees of freedom numerator equals 3. The corresponding value of F is 99.17. All right. On to the next section. Okay, testing two variances, section 10.4. Go ahead and check out your focus points. Sorry for any typos in the PowerPoint. At this point, you know I did not make them. In this section, we present a method for testing two variances, or equivalently two standard deviations. We use independent random samples from two populations to test the claim that the population variances are equal. The concept of variation among data is very important, and there are many possible applications in science, industry, business administration, social sciences, and so on. Excuse me, we have already tested a single variance. The main mathematical tool we used was the chi-square probability distribution. In this section, the main tool is the F probability distribution. Let us begin by stating that we need to assume for a test of two population variances. The two populations are independent of each other. Recall from section 8.5 that two sampling distributions are independent if there is no relation whatsoever between specific values of the two distributions. The two populations each have a normal probability distribution. This is important because the test we will use is sensitive to changes away from normality. How to set up the test. Get two independent random samples, one from each population. We use the following notation. Go ahead and pause the video if you need to figure out what these are. To simplify later discussion, we make the notational choice that, you can see it there. This means that we define population 1 as the population with the larger or equal, as the case may be, sample variance. This is only a notational convention and does not affect the general nature of the test. Step 2, set up the hypotheses. The null hypothesis will be that we have equal population variances. Reflecting our notation setup, it makes sense to use the alternate hypothesis as one of the following. Notice that the test makes claims about variances. However, we can also use it for corresponding claims about standard deviation. Step 3, compute the sample test statistic F. For normally distributed populations with equal variances, the sampling distribution we will use is the F distribution. See table 8 of appendix 2. The F distribution depends on 2 degrees of freedom. You know this from the last section, numerator and denominator. Find or estimate the p-value of the sample test statistic. Use the F distribution to find the p-value of the sample test statistic. Oh. You need to know the degrees of freedom for the numerator and the degrees of freedom for the denominator. Find the block entries with your degrees of freedom as row header and your degrees of freedom for the numerator as column header. Within the block of the values, find the position of the sample test statistic F, then find the corresponding right tail area. Okay, so they're just showing you this again. The interval containing the p-value for F equal to 55.2 is between 0.010 and 0.025. The table 1016 gives a summary of computing the p-value for both right-tailed and two-tailed tests for variances. Right-tailed test is given here. And of course, you cannot see the two-tailed test. I apologize. You will have to look in your book. Okay. All right. Prehistoric Native Americans smoked pipes for ceremonial purposes. Most pipes were either carved stone pipes or ceramic pipes made from clay. Clay pipes were easier to make, whereas stone pipes required careful drilling using hollow core bone drills and special stone reamers. An anthropologist claims that because clay pipes were easier to make, they show a greater variance in their construction. We want to test this claim by using a 5% level of significance. Data for this example was taken from Wind Mountain Archaeological Region. Assume the diameters of each type of pipe are normally distributed. There's your information. Here they're going to check their requirements. Using a calculator, verify the following. Or any other statistical software you would like to use. Note, because the sample variance of ceramic pipes is larger than the sample variance of stone pipes, we designate population 1 as ceramic pipes. Set up the null and alternate hypothesis. The null hypothesis states that there is no difference, while the alternate hypothesis supports the anthropologist's claim that the clay pipes have a larger variance. The sample test statistic F is equal to 4.496. Okay. All right. Find the interval containing the p-value for F equal to 4.496. This is a right-tail test with degrees of freedom. So 10 and 8. And you can go back to the other slide if you need those. Degrees of freedom for numerator was 11 minus 1, which is 10. Denominator, 9 minus 1, which is 8. So the interval is between 0.010 and 0.025. Conclusion, since the p-value is less than alpha, we reject the null. With technology, you can find that the p-value is roughly 0.0218. At the 5% level of significance, the evidence is sufficient to conclude that the variance for the ceramic pipes is larger. Go ahead and pause the video for the procedure. All right. One last long section.